In the next subsection, I want to look at the string matching problem again. We've just covered a lot of algorithms for string matching in the last section, but they were all sequential. We didn't care about parallelism. It turns out this is a nice problem to get started. And the reason for that is that some problems are really easy to parallelize. And we call those embarrassingly parallel. It's a kind of a cute term, but is one of those vague things again. There's a way to split the algorithmic problem into small subtasks. And each of these subtasks must be computable, solvable, independent of all the others. If a problem is like that, you can just assign all the subtasks in parallel to different processing elements, and then you get a huge speed up from the parallelism. A typical example that's clearly like that is if you have two large matrices and you want to compute the sum. I'm not talking about matrix products for now. If you just do the sum, remember sum of matrices is just the element-wise sum. So every element, every entry in the output of this algorithm is depending on two things in the input, and it's not talking to any of the other subproblems. In a way, matrix multiplication is similar. You can also compute those in an independent way, but the smarter algorithms for matrix multiplication don't do that. They try to reuse some information. Whereas for the sum, there's nothing to be gained. It's easy enough as it is. Such an embarrassingly parallel algorithm, embarrassingly parallel problem is the best case for parallel algorithms. Then there's not much that you need to think about. Unfortunately, most problems aren't like that. And I think it's insightful to think about sorting. Again, we've talked about that at length in the unit before the last one. We didn't care about parallelism at the time. But if you think about this task of rearranging elements in a list into sorted order, it's not so clear what an individual subtask would even be. We had divide and conquer algorithms, so they started with breaking things in half, and then that was subtasks. But it's really not so clear how you can define small subproblems that are also independent of each other. We'll see that some parts are like this, but you need to work your way around them. It's not obvious. So sorting is not necessarily one example of such a problem. How about string matching? Without telling you anything about the problem and how you potentially could solve this, I will just ask the question now, and we'll come back to that later. I don't want to show the answer yet, but okay, well, I'll wait till we have 40 or so. And then I'll just lock the question this time for the pedagogical effect of looking at it later. So if you want to cast your vote, do it in 5, 4, 3, 2, 1. And because the live stream is 5 seconds delayed, as if it means, so let me talk and waffle around for a while. 3, 2, 1, locked. All right. We'll come back to it. So it's an interesting case. We've seen a lot of algorithms. in a way, all the algorithms for string matching that were particularly good according to the metric of unit 4 were exactly the ones that exploited maximally the knowledge from the previous step. Remember, we had character comparisons was what we counted, and we tried to not do redundant comparisons. But by the essence of a non-redundant comparison is one that we haven't seen, and redundant was we build on the knowledge we have. So it's kind of the opposite of this inherently or embarrassingly parallel. It sounds like this is exactly not what you want to do. So we might need different algorithms. Before we dive into the problem a bit more, I want to rephrase it that makes it a little more natural and simple for parallel algorithms. It won't at the end affect the vote that we've had, but makes it a little cleaner. Unit 4, we said string matching is find the first occurrence of the pattern in the text if there's one. Now I'll say just report all. And the reason is then we don't have to communicate between the processing elements to find out if we should answer no. If any of those solves a subproblem and doesn't find an occurrence of the pattern, it would have to ask all the others, hey, did you also not find a pattern? And only if everyone says no, 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 then you can report no match. To avoid us that hassle, to spare us from that hassle, I'll just say everyone reports a match if they find one. And if not, the user will have to figure it out later. That's a bit more natural in the parallel setting. And then it's natural to define subproblems as checking individual guesses. So we have some way of defining subproblems that comes from string matching. And we could say that checking of one guess is a subtask. So let's try the easy thing. Let's go back to the brute force algorithm for string matching. I've copied this on the slide. It's almost literally the same as what we had in the last unit. What I added, obviously, is the red part. I'll comment on this type of parallel pseudocode in a second. One thing that I took out was the sequential brute force method at the end had, if none of the iterations returned a match, then there was this return no match. We don't do that here. So the type of code we write for these parallel algorithms will usually be a for loop or something similar like this. And we just tack on this keyword in parallel, which is supposed to mean all these iterations of the for loop, this inner part, that's repeated many times. Sequentially, we just go through all the different values of I. But now if I write in parallel, the understanding is we can do all of these, each on a different processing element. And the index, the loop variable, gives us the index of the processing element. This inherently requires that all the iterations of the loop body can be done independently. If they cannot, if they build on each other's computation and you don't pay attention, that's your problem. This is similar to if you have programmed in OpenMP, you may recognize that this is precisely one of the things that OpenMP can do for you. And there's all sorts of caveats. If you use this without too much thinking, then things can go wrong. That's in a way the same with this pseudocode. The inner loop hasn't changed. So each individual processing element is getting some index I, a guess, and then it just goes through the pattern and checks if it matches all along. And instead of returning, I just say report a match at I. That's some vague intermediate stage. What we would really need is another thing, another step afterwards that collects the results. This is a problem we'll talk about later, so I'll leave that out. Long discussion for a simple algorithm, but I wanted to make sure that the parallel pseudocode is clear. So if you have questions on how the code is supposed to work, or what is supposed to mean to write a loop like that in parallel, then let me know or ask. The other question is, how good is it? And remember, we'll have two measurements of time, span and work, or time and work. That's one of those slides where I wrote time, but it's parallel time or span all the way through. What's the time for executing this algorithm? Usually when you see a for loop, you think, oh, this is so and so many iterations, but haha, it's in parallel, so it doesn't count. Each of these steps is done in parallel, so we only really look at what does the longest of these iterations, how long does the longest running iteration take? And that's a loop over the pattern, so it takes time linear in the size of the pattern, theta of m. Now this is if you use the code as given. You'll see in the tutorials that for this task of checking whether two strings are equal, you can actually do better depending on the machine model. If you allow some concurrent accesses, you can do this much faster, which is an interesting speed up at that point. Unfortunately, it's all not really that useful because work is really poor. If you sum up the work that you do, it's in the worst case, you do m comparisons in each loop iteration, and you do this across roughly n processing elements. So this is, in a way, like the brute force method used for sequential algorithms, for the sequential brute force algorithm. And we've discussed at length in the last section that there's much better solutions than, for the worst case, than the brute force algorithm. So work is not good. Time is great. You can't possibly beat constant time. But if you remember Brent's theorem from a few slides back, unless you have absurd numbers of processing elements, that won't help you. If work is bad, the overall time is still slow. Maybe we can do something else. And of course, we'd like to take advantage of all this fast sequential string matching that we've developed. And it turns out a fairly general technique works here as well. You can use blocking. You can break the problem in a different way into subproblems. And that allows you to improve the work. So what we'll do is we split the text into overlapping blocks so that we never miss a character. So let me illustrate this on a quick example, just graphically. So then I think it's clear why we do that in exactly this way. It doesn't need a power of 2. So that's your text T. And I don't care about the actual letters here. It's just conceptual picture. And let's say m is 3. So the pattern could occur here, or it could occur here, or it could occur here at any of the positions, right? It's wherever you have a 3-character long stretch, that could be one occurrence of the pattern. What we want to do is to use a fast sequential algorithm for a small section of the text and check if the pattern is in there. And the trick here is that works basically out of the box, but you have to make the portions of the text slightly overlapping. So that the length of the overlapping parts is 2m minus 1. This is 5. And so the first 5 are assigned to one processing element. So all of these red ones will be caught by the first processing elements. If there's an occurrence, it will find it. Now, how about an occurrence that spans this boundary that might not be caught? That should go one further. We have to catch the orange ones as well. So we overlay a second one, starts at m, and also goes 5 long. And this will cover all the orange ones. And then for the next red one, which again would escape this one by 1 character, you have another start. So you start at 0, at 3, and then at 6 again. And so that red one would be caught by that one. Okay, so it's a simple picture proof that no matter what you do, one of the blocks will always see an occurrence of the pattern if there is one. With that preparation, the algorithm is really simple. You just iterate over all the block IDs if you want, and compute what is the portion of the text you have to look at. That's these 5 characters in our example. And you can use, say, the KMP algorithm to check if the pattern occurs in there. Now, this just to save effort, I stored the result. If KMP finds no match, then you don't report anything. But if it does, then you report the result. So probably clear. Is it clear to you guys that the algorithm works correctly? There's basically two things. It should never report a match that's not really in the text. That won't happen because it's looking at a substring of the text, and it only says, yeah, there's a match if I found the pattern there. The other thing is it cannot miss a match. That's what I tried to prove with this picture. No matter where the match starts, one of the blocks will entirely contain that these M positions, and so we'll have to find the match. Again, second question, how good is this algorithm? If we look at the time, again, parallel time means this parallel loop doesn't count. It's happening all at the same time. So we just have to find out how long the loop body takes. We call the KMP algorithm, which we know has running time n plus m for a text of length n and a pattern of length m. Now, we're not using it on the full text, but on a small snippet. So if you insert that, you get overall linear time in terms of the pattern, so a theta of m, because we use it on a very small piece of the text. And if you compute the work, is also work efficient. The reason is that we have not so many blocks. So even though each block uses theta m effort, we only have n over m roughly, plus 1 maybe. That's still theta of n overall effort, overall work. At least if you assume that the pattern is shorter than the text, that's work efficient. And maybe a simple check can catch that corner case. So that's great. We have a work efficient algorithm now. But we've already seen on the last slide that the parallel time m is not the best possible. We've had a better algorithm just where the work was crap. So if we come back to this question, the correct answer is the third one, which a few of you got. Okay, interesting rendering of this character. It's embarrassingly parallel in the sense that you can solve it as efficiently as possible, so that the total time is dominated by the work efficient part. If the length is much longer than m, then you can say that this parallel time theta of m is not bothering me too much. The overall work divided by the number of processing elements that I have is probably dominating this. And so there I would say it's embarrassingly parallel. Turn the argument around and it's clear that it cannot be yes. If the pattern and the text have roughly the same length, what you would get in this case here is parallel time stays the same and work stays the same. So you don't speed up at all over the sequential algorithm. And so that's work efficient, but not really parallel. You haven't sped up anything. So in a way, it's easy to parallelize string matching only for short patterns. That is all I want to say about the simple string matching methods that we'll look at in detail. The two things I showed you, the code is really simple. It's also reasonably efficient to implement. You could even distribute the text and it would still work. But when the pattern is also long, it might not be so helpful. So you could ask, could you improve on this? Can we get work-efficient methods where the span is also better than m? So we can really parallelize somehow non-trivial this matching part. This is only possible if we can parallelize the matching process. That we can do if it's just checking two strings for equality, but the pre-processing of the pattern is also part of this. And as far as I know, this is not possible with easy methods. But people have figured out more complicated ways to do that. I skipped those here. If you're interested to see a part of this more complicated algorithm, you can check out the recordings from last year. But I took it out in favor of some other things, also because it was not the entire story. There was always the pre-processing missing, which is much more complicated. So it was never so satisfying for me to teach that, showing you this nice, lovely bit that I could explain and then leaving off with this black box that we didn't dig into. Now the black box is just a bit bigger. But I want to mention, at least in theory, you could solve the problem faster. You can do log m times. That's, again, an exponential improvement if you want. Even if the pattern's long, if you have this concurrent write, you can even do the matching part much faster. For the pre-processing part, there seems to be a barrier, a lower bound that you cannot do it in constant time, even if the machine allows you concurrent writes. And again, no details on that. Just so that you don't walk away and say, oh, all the simple methods don't work, so nothing works. That's not quite true. In terms of the practicality, I'm not sure if these methods ever have been implemented. So that's maybe the statement to make.